Since the whole idea of place value is so important, and because it's a little bit tricky to fully understand, we're going to do a little bit of a review of what place value is really all about. So let's start with our own base 10 number system. We know that when we count 1, 2, 3, 4, 5, 6, 7, 8, 9. But then when we get to the number that we know of as 10, we use 2 digits to represent that. Each of those digits individually has a meaning. We have a 1 and a 0, but together they mean something completely different. The 0 means we have 0 ones, and the 1 means we have one group of 10. So we've filled up our hands. We have one group of 10 fingers. If we think about that idea of grouping in base 10, and we wanted to count the smileys, what we would have to do is group 10 at a time, and then look to see if we have any single smileys left over. And in this case, we have one group of 10 and 4 single smileys left over, so this represents the number 14 to us. So in our base 10 number system, we have 10 allowable digits, 0 through 9. We do not have a single digit for the number 10 because once we get to 10 objects, we're going to group them together. If we look at this number in base 10 and think about its place value, we know that furthest to the right we have ones. The next place to the left of that is the tens place. The next place to the left of that is the 10 squared or 100s place. And then if we group 10 of those hundreds together, we have thousands. And if we group 10 of those thousands together, we have 10,000s. So this number that we know of as 24,123 really represents 2 groups of 10,000, 4 groups of 1,000, 1 group of 100, 2 groups of 10, and 3 groups of 1. That's what we said we would call expanded form for a number. And we also saw that we can use expanded form for numbers in other number bases as well. So let's think about another number base. What if we only had one hand? Well, then we might count a little bit differently. We'd probably still count 1, 2, 3, 4, but when we're ready to fill up that hand, we would call that 1, 0. Now remember, we don't want to call this 10 because that has a particular meaning in a base 10 number system. We're going to call this 1, 0 because it represents one group of 5 and no ones. So let's think about a base 5 number system. If we had our smileys and we wanted to group them in base 5, that means we would group 5 of them together at a time. And then if we did that, we would have 2 groups of 5 with 4 ones left over. So that would represent the number 24 base 5. Don't call it 24 because 24 means 2 tens and 4 ones. This is actually 2 5s and 4 ones. So we're going to call it 24 base 5. In a base 5 number system, there are 5 allowable digits, which are 0, 1, 2, 3, and 4. There is no 5 in a base 5 number system, no digit for 5, because if we're trying to represent 5, we would group those 5 together and we would call that 1, 0. If we have this number in base 5, we would say 2, 4, 1, 2, 3, base 5, and we want to know what this means to us in our base 10 number system. We would have to think about base 5 place value. Furthest to the right, we have ones. To the left of that, since we're grouping by 5s, we have groups of 5. To the left of that, we have groups of 5 5s, which would be groups of 25. To the left of that, we would have groups of 5 25s, which is 125s. To the left of that, we would have groups of 5 125s, which is 625, and we could continue this as long as we needed to. So this number, 2, 4, 1, 2, 3, base 5, to us in our base 10 number system is 2 625s, 4 groups of 125, 1 group of 25, 2 groups of 5, and 3 groups of 1. So that's still considered expanded form. It's expanded form in a base 5 number system. Now, if we want to know what that means to us in base 10, we can go ahead and do the multiplications and the addition, and we'll find out that this number to us represents the same thing as 1,788 in base 10. If we have the number 203 in base 5 and we want to change it to a base 10 number, we can just remember what place value means in base 5. We have a 3-digit number. Rightmost digit represents ones. The digit to the left of that represents groups of 5s. The digit to the left of that represents groups of 5 5s or 25s. So this number is 2 groups of 25, no groups of 5, and 3 groups of 1, which to us would be the number 53. Now let's look at some pictures to make some sense of this, because just because we represent a number in a different number base, that doesn't mean it represents a different value. We start off with 203 base 5, which is 2 groups of 25 and 3 ones. So if you look at the number of squares we have here, this is what a base 5 person would do to group this, to identify the number that's being represented. So they would say 2 groups of 25, 3 groups of 1, that's 203. In our base 10 number system, we would take these same squares and we would regroup them into groups of 10. So we would do something like that, and we can see that we now have 5 groups of 10 and 3 ones, which to us in our base 10 number system is 53. It's the same number of squares, we've just grouped them differently, grouping them by tens for our base 10 number system. Let's look at some other number bases and see what the grouping is like in those other bases. So for a base 4 number system, there's only 4 allowable digits, which are 0, 1, 2, and 3. There is no digit for 4 in a base 4 number system. Place value for a base 4 number system would start off with the rightmost digit representing ones, and since we're grouping by 4s, the next digit to the left would be groups of 4. The next digit to the left of that would be groups of 4 4s or 16s. To the left of that is groups of 4 16s or 64s. To the left of that is groups of 4 64s or 256s. So this number 20213 base 4 means we have 2 groups of 256, no groups of 64, 2 groups of 16, 1 group of 4, and 3 groups of 1, which to us in our base 10 number system is the number 551. How about a base 7 number system? The allowable digits in a base 7 number system would be 0, 1, 2, 3, 4, 5, and 6. 7 digits starting with 0. The number 7 to us is not in a base 7 number system. If we have this number, 261 base 7, and we want to determine what it would be in a base 10 number system, we're going to think about base 7 place value. So in base 7, the rightmost digit is 1. To the left of that we have groups of 7. To the left of that we have groups of 7 7s or 49s. And then we have groups of 749s, which is 243s. And then we have groups of 7 243s, which is groups of 2,401. And this number is only a 3-digit number. So we're going to look at 261 base 7 as 2 groups of 49 plus 6 groups of 7 plus 1 1. In our base 10 number system, that would be the number 141. Base 12 is a tricky one because in base 12 we have 12 allowable digits. The digits from 0 to 9 are familiar to us, but we need a single digit to represent what to us is 10 and 11. So we'll use T for 10 and E for 11. If we have this base 12 number, 2TE, and we want to write it as a base 10 number, we need to think about base 12 place value. Furthest to the right is the ones. If we group 12 ones together, we have 12s. If we group 12 12s together, we have 144s. If we group 12 144s together, we have groups of 1,728. If we group 12 1,728s together, we have groups of 20,736. But this is only a 3-digit number. So we look at the digits in each of the places, and we can see we have 2 groups of 144, 10 groups of 12, and 11 groups of 1, which to us in base 10 is the number 419. Now if we can take a number that's in one of these other number bases and rewrite it as an equivalent number in base 10, we can certainly go the other direction. So let's start with 281 base 10 and think about how to write that as a base 5 number. If we remember base 5 place value, we can determine how to regroup these numbers into groups of 5 or 25 or 125. We don't have enough to group 625 together, so we're not going to have a 5-digit number here. We're going to have a 4-digit number. So let's start with the 4th place from the right, the 125's place, and look at how many times we can find a group of 125 within 281. Well, that would be twice, because 2 times 125 is 250. So if we take 250 of these items and group them together, we have 2 groups of 125, which means we still have 31 left to regroup into groups of 5 or 25. Well, let's look at the 25s. We're going to go for the largest group we can find next. There's one group of 25 in the 31. That would leave us with 6 more. Now we've got groups of 5 to try to find, and there's one group of 5 in the 6, and that leaves us with 1 left over. So 281 base 10 is the same thing as 2111 base 5. Let's go from base 10 to base 3. In base 3, the place value starts with 1 furthest to the right, and then we have groups of 3, groups of 9, groups of 27, groups of 81. It looks like we do have a group of 81 inside the 97. We have one group of 81. That would leave us with 16 left to try to regroup. Now the next place value that we're looking at in our base 3 number is 27s, and we don't have any groups of 27 in 16. But then we can look for groups of 9. There's one group of 9 in that 16. That would leave us with 7 more. Inside that 7 that we have left, we can find 2 groups of 3. That's 6. That would leave us with 1 more. And that 1 more is that one group of 1 that's left. So 97 base 10 is the same thing as 10121 base 3. And now base 12. So for 281 base 10 to be rewritten as a base 12 number, we need to remember base 12 place value. Remember, place value always starts with 1s furthest to the right, and since it's base 12, we're going to group 12 of those 1s together, group 12 12s together, group 12 144s together. This number that we're trying to write in base 12 is 281. So we don't have enough to group together to make a group of 1,728, but we can certainly find at least one group of 144. Let's see, can we find two groups of 144? I don't think so. 2 times 144 is 288. We can only find one group of 144 inside that 281. That leaves us with 137, which we have to try to group into groups of 12. There's 11 groups of 12 in 137 because 11 times 12 is 132. And that would leave us with 5 more that would be ones that could not be regrouped as groups of 12. That gives us 1E5 base 12 as being equivalent to 281 base 10. The other thing we're going to talk about is addition and subtraction of whole numbers. So for the rest of this discussion, we're going to look at just base 10 numbers, but we will be applying what we're doing here to numbers in other number bases. But for now, just think about base 10 numbers. The natural numbers, the counting numbers, start with 1 and then 2 and then 3, and they continue forever. The whole numbers include the natural numbers, the counting numbers, and also include the number 0. For what we're going to talk about right now with addition of whole numbers, we are only looking at these whole numbers to add. Now we know as adults that there are many other numbers apart from whole numbers. There are negative numbers that would be included with the integers. There are fractions that would be included with the rational numbers. There are irrational numbers, things like the square root of 2. We're going to pretend that we do not know about those numbers at this point. So our world of numbers at this point is just going to be these whole numbers. You might think about the fact that the natural numbers are a subset of the whole numbers. So if a number is a natural number, it is also a whole number. So let's start with whole number addition. And think about what we call these pieces that we're adding together when we do an addition problem. The two numbers that we're adding are called add-ins. And the number that results when we add these two numbers together is called the sum. Sum is probably a familiar word to you. Add-ins might be one that you haven't heard for a while. We're going to look at some models for whole number addition, ways that we can demonstrate how addition works. And we're going to use this same problem, 2 plus 3 equals 5, to illustrate those models. One model is called a set model. And a set model literally makes sets of objects and shows what happens when we combine them with addition, which means we put the sets together. So if we're adding 2 and 3, we might show a set of 2 objects and another set of 3 objects. This is something you could do very easily in a classroom with maybe blocks. You could have a set of 2 blocks and a set of 3 blocks, and then you would combine the 2 blocks and the 3 blocks in their individual sets to make one set of 5 blocks. So for a set model, we're showing these individual add-ins being combined, literally combined, think of it as physically combined, to give us another set that is our sum. Another model that we can use is called the number line model. Now remember, at this point, we're only dealing with whole numbers. So our number line is going to look a little bit different than a number line you think of. Our number line's only going to start with 0, and then it's going to only have on it the whole numbers. So even though as adults we know that there are numbers in between these numbers, we're going to pretend they don't exist. So to demonstrate 2 plus 3 equals 5 with a number line model, we start with 0, and then we draw an arrow that's 2 units long. And then we add to that, append to that from its end, an arrow that is 3 units long. And we look to see where that last arrow is pointing. It's pointing to the 5. So 2 plus 3 equals 5 because we can combine these two arrows and end up with an arrow that's pointing to the number 5. There's some properties of whole number addition that you're probably familiar with, but you may not be completely familiar with the names. There is a commutative property of addition, which says that we can add numbers in any order and still have the same sum. There's an associative property of addition, which says we can group numbers in any order and still have the same sum. And there's an identity property of addition, which says that we can add 0 to any number and still have that same number we started with. 0 has a special name then because of this property. It's called the additive identity. 0 is a number that we can add to any number and not change the value of that number. So let's extend what we just talked about a little bit to subtraction of whole numbers. If we look at a subtraction problem, a subtraction sentence, we can name the parts of that subtraction sentence. The 5 in this case is called the minuend. With subtraction, we're always going to start with some amount. So we're starting with this 5. And then what we're subtracting is called the subtrahend. And the result of that subtraction is called the difference. There is a relationship between subtraction and addition. For example, in this problem, 5 minus 2 equals 3, that is only going to be true if 5 equals 2 plus 3. So sometimes it's a little bit easier for children to understand what they see in a subtraction problem if they rewrite it as an addition problem. And you'll also see that this relationship between subtraction and addition becomes important when children are using inverse operations to solve equations, which is something that will need to be done when they're in algebra. Let's look at some models for whole number subtraction. And we'll use this subtraction problem as our illustration. Starting with a takeaway model. So for a takeaway model, we're going to imagine that we have a set of objects that has 5 stars in it. And then the subtraction we're going to think of as takeaway. So 5 minus 2 means 5 take away 2. So we're going to take away 2 of the stars. Now if these were actual objects, we could literally take them away. If these were blocks, we could take away 2 blocks. But in our case, since we can't really do that with our picture, here's how we're going to show that we've taken away the 2 stars. And then we have 3 stars left. So that's how we get the difference. 5 minus 2 is 3 because we have 3 stars left when we take 2 stars away from the 5 stars we started with. Another model we can look at is the missing addend model, which takes advantage of this relationship between subtraction and addition. So if 5 minus 2 equals something we don't know, then 5 equals 2 plus that something. So this unknown quantity is 3. So we can actually find this answer to our subtraction problem by looking at it as an addition problem. That's another look at numbers in other number bases and a little taste of some models for whole number addition and whole number subtraction. The next thing we're going to do is look at some of those operations using numbers in other number bases.